Hi, I'm Professor Kelly, and this is a lecture on infinite lists for the functional paradigm. The learning goals for this lecture are to be able to implement finite lists using first, second, last patterns, and implement infinite lists using first, second patterns, to employ the take function in Haskell to get part of an infinite list, and to apply list comprehensions and list patterns to create infinite lists, and to define streams and apply a stream with a starting number to create infinite lists. We can define a list over a range of integers using this notation in Haskell: a square bracket followed by the first number in the list, and then two dots, and then the last number in the list. Haskell assumes you will want a list of integers that start at the first number and end at the last number and go up by 1. For example, if I type 1 to 10, it gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I type first, second, dot, dot, last, it assumes that the difference between the first and the second numbers in the list indicates the step size, and so it will go up by a constant step size according to that difference. For example, if I do 2, 4 to 10, it will give me 2, 4, 6, 8, 10, going up by 2 each time because 2 and 4 are 2 apart. If we use first, second, third, and then dot, dot, last, we get an error. Haskell does not know how to interpret having a third item in the list like this. So just give it first and last, or first, second, and last. So the funny thing about Haskell is that the last value is actually optional. We can create infinite lists by not specifying an endpoint. For example, if we go 1 dot dot, Haskell will happily assume that we are creating a list that starts at 1 and goes up by 1 forever. This will give us all of the counting numbers up to infinity. If we create a list 1, 1 dot dot, it looks at the difference between 1 and 1, which is 0, and so the step size is 0. It will create a list of 1s that continues on to infinity. 2, 4 will give us 2, 4, 6, 8, 10, 12, the even numbers. 1, 3 also has a step size of 2, but because it starts at 1, it gives us the odd numbers. 4, 8 gives us the multiples of 4. If we try to print an infinite list, Haskell will start happily printing it and will continue printing it forever until you hit Control-C and stop it. To use lazy evaluation to process only part of a list, we can use the take function, which is built in Haskell. Take has two parameters, an integer, n, that specifies how many items you want to take from the start of a list, and the list itself that you are taking from. It returns the n elements from that list. The base case is if you have an empty list, take returns an empty list. Or if you have no elements that you want to take from the list, it will return an empty list. In the recursive case, we're taking n elements from the list, we split the list into head and tail, and then we concatenate the head to the start of the list and apply take n-1 to the tail. For example, let's say we do take 5 of the list of multiples of 3. This will give us 3, 6, 9, 12, and 15. A stream is a function that returns an infinite list. Streams are recursive functions with no base case. In most languages, a stream would simply be an error. No base case, it's not a proper recursive function. However, because Haskell uses lazy evaluation, as long as you stop the stream at some point, you're actually going to be just fine. For example, let's define the stream plus 2. It takes an integer and returns a list of integers. It's going to take a starting number n, and then it will call plus 2 on n plus 2 and concatenate the two. This will create the infinite list starting at the starting number and going up by 2. Let's take a look at an example. We can do take 5 plus 2, 1. Plus 2, 1 tells plus 2 to start at 1 and then go up by 2's. Take 5 says only give me the first 5 elements from the infinite list defined by plus 2. We get 1, 3, 5, 7, 9, the odd counting numbers. We can define a function called odds that will give us all of the odd numbers. It takes no parameters and returns a list of integers, the odd numbers. We define odds as call plus 2 with the starting value of 1. So if we do take 5 odds, we get 1, 3, 5, 7, 9 again. We can also define one for even numbers. Evens equals plus 2 starting at the number 2. If we do take 5 evens, we get 2, 4, 6, 8, 10. List comprehensions can also be used to produce infinite lists. For example, if we use the list pattern starting at 1 and going on to infinity, we can embed that inside of a list comprehension. This list comprehension is not terribly interesting. It's just the identity list comprehension, and so it's really just going to return 1 dot dot, basically all the numbers starting at 1 and counting up to positive infinity. We can also define a list comprehension that gives us the odd numbers. We're taking the list pattern here 1 dot dot, again giving us the numbers from 1 all the way up to positive infinity with a step size of 1. We take each of those numbers and we check to see if it's divisible by 2. If it isn't, then it goes into the odds list. Again, this isn't terribly useful as a list comprehension because we could do the same thing much more succinctly as just 1, 3 dot dot, which would also give us the complete list of odd numbers. Here's something you can't do just using a pattern though. Here we're getting a list of all the square numbers. We do so by taking all the positive integers and squaring them. This will give us the list 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and so on. You cannot do this simply using the first, second format because the size of the step between the numbers changes. From 1 to 4, it's 3. From 4 to 9, it's 5, and so on. Consider the Fibonacci sequence, where each number is the sum of the previous two numbers in the sequence. How can we represent this infinite list in Haskell? Can we write the Fibonacci sequence as a lazy list pattern in Haskell? Well, if we try just putting the first two elements of the Fibonacci sequence and go dot dot, we'll just get an infinite list of ones. If we try giving it the first three numbers of the Fibonacci sequence, 1, 1, 2, dot dot, well, Haskell doesn't actually like it when you give it the third number in a sequence like this, so this gives an error. So we cannot use a lazy list pattern because the difference between numbers is not constant. Can we write it as a list comprehension instead? Well, let's try. We know that new elements of the Fibonacci sequence are x plus y, and that we know the starting values are 1 and 1. So what happens if we do x plus y, where x is in the list 1, 1, and y is in the list 1, 1? We get, instead of the Fibonacci sequence, an infinite list of 2's. The problem here is that we cannot use a list comprehension because the next number in the list in the Fibonacci sequence depends on the two previous numbers in the same list rather than on some other list, such as the infinite list of ones. Can we write a stream? We can absolutely write the Fibonacci sequence as a stream. We'll need two functions to do so. The first function just gets the Fibonacci sequence started. It returns the Fibonacci sequence but doesn't take any arguments. To start the sequence, we put 1 and 1 at the beginning of the list. The remainder of the list is going to be defined by another function called fibs prime. We call fibs prime on the first two numbers in the Fibonacci sequence. Fibs prime takes two parameters and returns the list of Fibonacci numbers that follow those two parameters. To define the Fibonacci sequence, It adds the two parameters and then calls fibs prime again on the next two numbers in the sequence. So if the current two numbers are x and y, the next two numbers are y and x plus y. Let's see this demonstrated. Take 10 fibs. We get 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, the first 10 numbers of the Fibonacci sequence. The sieve of Eratosthenes is an ancient algorithm attributed to the Greek mathematician Eratosthenes of Cyrene in 300 BCE. This algorithm allows one to find all the prime numbers starting from 1 up to some specified range. It can be implemented as a stream. We start by identifying 2 as a prime number. Then we eliminate all of the multiples of 2. We then identify 3 as a prime number and eliminate all of the multiples of 3. We move on to 5 and eliminate all of the multiples of 5 from the range. Then we eliminate the multiples of 7. At this point, we identify 11, 13, 17, 19, and so on as prime numbers. These don't have multiples within the range 1 to 120, but we would eliminate their multiples if they had any. The sieve of Eratosthenes takes a list of integers, the range over which we wish to find prime numbers, and returns a list of integers, the prime numbers we've discovered. Because this is a stream, we don't need a base case. We split the list into head and tail. We add the head to the beginning of the list. It's prime. We do two things to the tail. The first thing we do to the tail is we eliminate all of the multiples of x from the tail. And then we call sieve on the tail. Sieve will go on to find more primes and eliminate more of the multiples of those primes. To get the list of primes, we need a second function. This function primes takes no parameters and returns the whole list of primes, which is infinite. To do so, it calls sieve and calls sieve specifically on the range of numbers starting at 2 and going on up to positive infinity. Let's see this in action. Let's take 10 primes. This will give us the first 10 prime numbers: 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Learning goals for this lecture are to implement finite lists with patterns. This is the form first, second, ... last. The second is optional. If you leave it out, Haskell will assume you're just going up by 1. For example, you could do 4, 8, ... 40 to get the multiples of 4 starting at 4 and going to 40. We can also create infinite lists in the same fashion, but by leaving off the last element. 4, 8, ... would give us all of the multiples of 4. We can use take to use this to get the first 10 multiples of 4. We can apply list comprehensions to get infinite lists that we can't create simply using the ... notation, such as squaring the numbers from 4, 8, and so on up to positive infinity. A stream is a function that returns an infinite list. We can use streams to define things like the Fibonacci sequence. Streams, generally speaking, will need a helper function or some sort of starting number in order to generate their infinite list.